Good afternoon, everyone. In this session, we'll be discussing the dual nature and the photoelectric effect, right? So we'll be mainly focusing on the previous year questions of dual nature and photoelectric effect. So I will be starting with the question number one, right? So the question number one is that the de Broglie wavelength associated with an electron accelerated by a potential difference of 81 volt is given, right? So let's first of all see how what is the equation of the de Broglie wavelength, right? So how so de Broglie wavelength is nothing, it's h upon p, where p is the momentum of the particle, right? P is the momentum of the particle or any body, right? So h is the Planck's constant, right? H is the Planck's constant. Now, lambda is equal to h upon p, right? Lambda is equal to h upon p. This is the de Broglie wavelength, right? Now we can write. We know that relation between kinetic energy and the momentum is that p square upon 2m, that's actually equal to the kinetic energy of the particle, right? Kinetic energy of the particle, right? That means that we can write momentum in terms of the kinetic energy. That will be p will be equal to under root of 2mk, right? So it means that we can write the equation of de Broglie wavelength in terms of the kinetic energy as well. That will be under root of 2mk, right? So this will be the what we call as de Broglie wavelength in terms of the kinetic energy, right? This is the de Broglie wavelength in terms of the kinetic energy, right? Now, now let's suppose if we accelerate an electron against a potential difference or with a potential difference of v volts, right? If an electron is there and it is accelerated because of the potential difference given to this electron, that's v volt, then because of the electric field, this electron is going to accelerate, right? Across the potential difference of v volts. Then the kinetic energy of this electron will be nothing. It will be the charge of electron multiplied by the potential difference, right? So the kinetic energy of this electron will be nothing. It will be charge of electron multiplied by the potential difference. This will be the kinetic energy, right? So it means that we can, in that case, we can replace the kinetic energy of the electron with 2 times m E multiplied by V, right? Now from here you can see here H is a constant, M is a constant, charge of electron is a constant. All the three are constant quantities, right? Constants, right? Now if we substitute all the values of these constants, H is the Planck's constant, M is the mass of electron, E is the charge of electron, right? So we'll get certain constant here, right? And that constant is nothing, that's 12.27 upon root of V, right? Upon root of V, right? And this wavelength is in the units of angstroms, right? This wavelength comes out in the units of angstroms, right? So the wavelength, de Broglie wavelength for an electron, when it is accelerated against a potential difference of V volts, it's given by this equation. Lambda is equal to 12.27 upon root V, where V is in volts, right? And this much angstrom will be the de Broglie wavelength, right? So now here in this case, it's given that its electron is accelerated against the potential difference of 81 volts. So it will be 12.27 upon 81. Root 81 is nothing, that's actually equal to 9, right? 9. So it will be approximately equal to 1.36 angstrom, right? 1.36 angstroms. So this will be the what we call as the wavelength, right? De Broglie wavelength. So for an electron, the de Broglie wavelength, or we can write it as lambda E. De Broglie wavelength of the electron will be nothing. It will be 12.27 upon root of V, right? Root of V. Similarly, you can calculate the de Broglie wavelength of proton as well, right? In that case, you have to replace m with the mass of proton, right? Rest of the things will be same, right? And you will also arrive at some results, right? But the most frequently asked question is that the de Broglie wavelength of the electron, right? De Broglie wavelength of the electron, that's 12.27 upon root of V, right? Or we can say the de Broglie wavelength of electron is nothing, it's inversely proportional to the root of V, where V is the potential difference, right? So this is how we can calculate the de Broglie wavelength of different objects, right? So in general, this is the general equation for the de Broglie wavelength h upon p, where p is the momentum, or in terms of kinetic energy, it's under root of 2mk, right? And in terms of accelerated potential, this is the relationship between the de Broglie wavelength and the accelerated potential, right? Now let's move on to the next question, right? Moving on to the question number 2, the maximum kinetic energy of the emitted photoelectrons in photoelectric effect is independent of, right? So we have four options: work function, intensity, frequency, wavelength, right? Now let's suppose we have this. Let's suppose this is the metal surface, right? If this is the metal surface, we are incidentting some photons or light on this metal surface, right? And because of this incidence, electron emission takes place, right? That's what we call as the photoelectric emission, right? And we know that the minimum energy required to for this emission to take place is what we call as threshold energy, or the frequency called as threshold frequency, or what we call as a threshold wavelength, right? So minimum energy required to so that electron is unbound from the metal surface, that minimum energy we call it as work function, right? We call it as work function, right? So it is necessary that maximum kinetic energy, we know that according to Einstein's equation, whatever energy we supply, right? Let's suppose H nu is the energy supplied to the metal surface. Some part of this energy will go into the work function, and rest of the energy will be as kinetic energy, right? So kinetic energy will be nothing, it will be equal to work function minus the total energy, right? So it will be total energy minus the work function, right? Here find out is the work function. Now it means that if we increase the work function, then the kinetic energy will actually decrease, right? Provided the frequency is fixed. So it means that the maximum kinetic energy will actually depend upon the work function, right? So it will depend upon the work function. Now the question is of intensity. We know that here you can see the kinetic energy no longer here depends on the intensity, right? It only depends upon the work function, and the work function itself depends upon the threshold frequency, right? Now you can see here that kinetic energy clearly depends upon the frequency of the incident ray of light and the work function of the metal surface. So intensity has no role to play in the maximum kinetic energy of the electron, right? So we can say the photoelectric effect is independent of intensity. It depends upon the frequency, it depends upon the wavelength, because we can write this kinetic energy as hc upon lambda minus phi naught as well, right? So it depends upon wavelength as well as work function and frequency, right? The only quantity which is only quantity in which the maximum kinetic energy does not depend is the intensity. So we can say that maximum kinetic energy of the emitted photoelectron is independent of the intensity in case of photoelectric effect, right? So let's move on to the question number 3, right? So question number 3 is that this is the one of the questions asked in your previous year exams, right? The work function of cesium, potassium, and sodium, right? These are the three alkali metals, right? Which have been given here, right? Uh, the work function of each of these metals is given that that's equal to 2.14 electron volt for the cesium, 2.30 electron volt for the potassium, and 2.75 electron volt for the sodium. And we know that work function is the minimum amount of energy. Work function is actually the minimum amount of energy that's required, right? Minimum amount of incident energy that's required so that the photoelectric emission just takes place, right? So that the photoelectric emission just takes place, right? So that minimum amount of energy, we call it as threshold energy, or threshold what we call as that's what we call as work function, right? That's what we call as work function as well, right? Or we can say it's the amount of energy so as to unbound an electron from the metal surface, right? It's the minimum amount of energy for any metal surface to unbound an electron on the metal surface. That's what we call as work function. And work function is different for different materials, and we have been given the work function for three different metals, right? And you can see here the minimum is here for cesium, and then we have potassium, then we have sodium, right? So it means that for cesium we need at least we need this much of energy to have a photoelectric effect, and for potassium we need 2.3 electron volts, and for sodium we need 2.75 electron volts respectively. Now the question in this question is given that the electromagnetic radiation has an incident energy of 2.2 electron volt. It means that we are only incidentally 2.20 electron volt of energy on the metal surface or on these photosensitive surfaces, right? Now the question is that which surface may emit electron? Which surface will emit electron, right? The only that surface will emit the electron for which the work function is equal to this incident energy or less than this incident energy, or we can say that phi naught should be less or equal to the incident energy, right? The phi naught should be less or equal to incident energy, then only the electron will be emitted from the photosensitive surfaces, right? Now you can see here 2.20 electron volt is the incident energy, but for cesium we need 2.14. It means that for cesium the photoelectric effect will take place, right? It means the cesium will emit the photoelectrons, right? But for potassium we need 2.30, right? But we have only 2.0, so it means that the potassium will not take in potassium the photoelectric effect will not take place, right? And similarly for sodium we need 2.75 electron volts for the sodium as well. No photoelectric emission will take place. So the only metal which will show the photoelectric effect will be the cesium, right? So only cesium will show the photoelectric effect, right? This was one of the questions asked in your previous exams, right? Now let's move on to the question number 4, right? The question number 4 is that the minimum wavelength of X-rays produced by an electron accelerated through a potential difference of V volts is proportional to, right? We have to find the minimum wavelength of X-ray produced by an electron accelerated through a potential difference of V volts. Now, we know that how X-rays are actually produced, right? This when electron is accelerated against the potential difference of V volts, right? The kinetic energy attained by this electrons will be nothing. It will be E multiplied by V. These will be the very fast moving electrons, right? With high kinetic energies, right? And these electrons will strike this target, right? This is nothing, this is the target, right? When the electrons strike the target, the electron will lose the energy, and this energy is emitted in the form of radiation, right? And these radiations we call it as these radiations are of high energy, extremely high energy, and these radiations we call it as X-rays, right? So this is how actually the X-rays are produced, right? Now we can, in this question, it has been asked that the minimum wavelength of X-rays produced, it means the maximum energy. Minimum wavelength means the maximum energy. So the maximum energy we can produce for the X-ray is that if whole of the kinetic energy of the electron is actually converted into the X-rays, right? Or we can say that the kinetic energy of the electron is EV, and it's actually converted into the light of X-rays, right? That will be equal to Hc upon lambda, right? Hc upon the lambda, and this will be the minimum wavelength, right? Minimum wavelength, because all of the energy of the electron will be converted into the X-ray, right? Now, lambda naught will be nothing. It will be actually equal to Hc upon Ev, right? Hc upon Ev. So this will be the lambda naught. So from here you can see here the minimum wavelength lambda naught for X-rays is actually inversely proportional to the V, right? It's actually inversely proportional to the V, right? So lambda naught is inversely proportional to V for the X-rays, and this is also one of the questions asked in your previous year exams, right? Now let's move on to the question number 5, right? So the question number 5 is that the light rays having photons of energy 4.2 electron volt are falling on a metal surface having a work function of 2.2 electron volt. The stopping potential of the surface is, right? We have to find the stopping potential, right? So the stopping potential is actually the potential required to stop the electron photoelectron of maximum kinetic energy, right? The minimum potential required to stop the electron of maximum kinetic energy, we call that as stopping potential, right? We call that as stopping potential. Now, in order to calculate the stopping potential, we know the maximum kinetic energy of an electron that can be is actually h nu minus phi naught, right? Where phi naught is the instant, phi naught is the work function, and h nu is the instant energy, right? Electromagnetic energy, right? The light rays having photons of energy 4.2 electron volts, so the incident energy is 4.2 electron volt, and the work function is 2.2. So that electrons will be moving with the maximum kinetic energy of 2 electron volt, right? And the potential required to stop these maximum kinetic energy moving electrons, right, is will be nothing. It will be 2 volts, right? If we apply a 2 volts of potential in the reverse direction, the electrons with maximum kinetic energy will stop its motion, right? So that's what we call as stopping potential. So that stopping potential here will be nothing. It will be 2 volts, right? Let's move on to the question number 6. The threshold frequency of a photoelectric metal is given as nu naught, right? If light of frequency 4 nu naught is incident on this metal, then the maximum kinetic energy of the emitted electron will be. The maximum kinetic energy is nothing, is actually the incident energy, right? E minus phi naught. Where phi naught is nothing, that's the work function. Now the uh, and work function is nothing, it will be h multiplied by the threshold frequency, right? H is the Planck's constant. Now you can see here the energy E, incident energy will be 4h times nu naught minus h times nu, right? So it will be equal to 3h nu naught, right? So this will be the maximum kinetic energy for the electron, right? So this will be the maximum kinetic energy for the electron with which it will be moving, right? Now let's move on to the question number 7. Right. The question number 7 is the number of photons per second on an average emitted by the source of monochromatic light of wavelength 600 nanometers, right? Of wavelength 600 nanometer when it delivers the power of 3.3 into 10 to the power minus 3 watt. Now, the power here means that the energy incident per second is actually 3.3 into 10 to the power minus 3 joules. So, this much of energy is actually incident on the metal surface per second, right? Per second, right? So, if per second, now we have to calculate the number of photons per second, right? Per second. And the energy emitted per second is 3.3 into 10 to the power minus 3 joules per second, right? So, it means there will be some 3.3 into 10 to the power minus 3 joules of energy, uh, right? It will be actually incident on the surface, and let's suppose n number of electrons, right? N number of n number of electrons, sorry, n number of photons are actually incident. So the energy of n number of photons will be nhc by lambda, right? So these are the number of photons emitted per second, right? So this is the energy, right? Or we can say the total energy is 3.3 into 10 to the power minus 3, right? So from here, what we have to calculate is that we have been given, we have to calculate the value of n, right? The value of h is given as 6.6 into 10 to the power minus 34, and it is 3 into 10 to the power 8 at the speed of light for the value of lambda. That's 600 nanometers. That will be 10 to the power minus 9, right? So from here, the value of n will be nothing. It will be equal to 3.3 multiplied by, it will be 600 into 10 to the power minus 12, right? Divided by 6 multiplied by 3 into 10 to the power minus 26, right? So this will be the value of n, right? Let's simplify it. So it will be 1, it will be multiplied by 2, right? So 2 into 3 will be 6. This and this will get cancelled. It will be 1 here, right? So it will be 100 multiplied by 10 to the power minus 12 upon 10 to the power minus 26, right? Or we can write it as 10 to the power minus 10 into 10 to the power 26. So it will be equal to 10 to the power 60. So the number of photons emitted per second on an average will be 10 to the power 16 photons per second, right? So number of photons per second emitted will be 10 to the power 16 photons, right? So this is how we can calculate the number of photons incident on the metal surface, right? So 10 to the power 16 photons will be incident per second, right? So let's move on to the question number 8, right? An electromagnetic wave of wavelength lambda is incident on a photosensitive surface of negligible work function, right? We can assume the work function to be very almost equal to 0, right? If m is mass of photoelectron emitted from the surface has de Broglie wavelength lambda t, okay, then relation between two is, right? So we know that the de Broglie wavelength is nothing, right? De Broglie wavelength is nothing. That's actually lambda is equal to h upon p, right? Or we can write it in terms of the kinetic energy. That will be equal to lambda upon under root of 2m right? Now you can see here on this metal surface, we're incidenting the ray of light or photons on this metal surface, and photoelectric emission takes place, right? Photoelectric emission takes place. Now it's given that the work function for this metal surface phi naught is equal to 0, right? It's negligible, right? It means whatever energy you are incidenting will be present as the kinetic energy of this electron, right? So we can say that Hc upon lambda, right? Hc upon lambda. Let me write this as lambda t, right? Lambda t. This is the de Broglie, right? So Hc upon lambda will be the energy incident, right? And whole of this energy will be present as the kinetic energy of this electron, because it's given that the work function is negligible, right? Negligible work function, right? We can assume the work function to be equal to 0 here in this case, right? If the work function is assumed to be equal to 0, right? So the total kinetic energy is actually equal to H upon lambda, right? H upon lambda. Now from here, what we can do here, if we square on both sides, for this equation, if you square on both sides, it will be lambda d square, it will be equal to h square upon 2m ke, right? Now let's take kinetic energy on this side, it will be h square upon 2m lambda t square, right? I can see here this kinetic energy and this kinetic energy, they are actually equal, right? So kinetic energy is equal to h upon lambda, and kinetic energy comes out to be h square upon 2m lambda d square. So from here, what we can do here, hc upon lambda will be equal to h square upon 2s m lambda d square, right? From here, h and h will get cancelled, right? So from here, the value of lambda, that's the wavelength of the photon, incident photon, in terms of the de Broglie wavelength of the electron emitted, photoelectron emitted, right? It will be equal to 2m, right? 2m lambda t square multiplied by c, right? Upon h, for h. So this will be the relation between the de Broglie wavelength and the wavelength of the incident ray of light. So this will be the relation between the de Broglie wavelength and the wavelength of the incident ray of light, right? Now let's move on to the question number 9. Moving on to the question number 9, a light of frequency 1.5 times the threshold frequency, right? It means that let's suppose if we have this metal surface and the threshold frequency is nu naught, right? This is nothing. This is the threshold frequency. It means that the minimum energy or minimum frequency that incident ray of light should have should be equal to nu naught, so that the photoelectric emission may take place, right? So an electron is accelerated from light of frequency nu naught, right? Light of frequency nu naught. Nu naught is the threshold frequency. Now, frequency of the incident ray of light is actually uh, 1.5 times the threshold frequency, or we can say incident energy is nothing. It's actually 3 by 2 times h times nu naught, right? So 1.3 times 1.5 times the threshold frequency, right? Now when the incident energy or incident frequency is 1.5 times the threshold frequency, then definitely photoelectric emission will take place, right, on the photosensitive material. But the question is, what will be the photoelectric current if the frequency is halved and intensity is doubled, right? Now the question is that what we do is that what we do is that we if the frequency is halved, right? The frequency is half of the initial frequency. It means that incident frequency was 1.5 times nu naught, right? So half of this will be nothing. It will be 0.75 nu naught, right? Now you can see here the incident frequency is actually less than the threshold frequency, right? The incident frequency is less than the threshold frequency. If the incident frequency of the electromagnetic radiation is less than the threshold frequency, then it's for sure that photoelectric effect will not take place, right? There will be no photoelectric emission, right? If there is no photoelectric emission, right? Photoelectric emission, no photo current will be there, right? No photo current, no photoelectric current. And we know that the minimum energy required to have the photoelectric emission, that's what we called as the threshold frequency, right? So threshold frequency, we should have threshold frequency so that the photoelectric emission takes place, right? And this is independent of the intensity, whatever be the intensity of incident ray of light. If the frequency of the incident ray of light is not at least equal to the threshold frequency, then whatever be the intensity, the photoelectric emission will not take place, right? So the answer to this question is that no photoelectric current will be there, right? There will be no photoelectric current at all, right? Because the incident ray of light now have the frequency less than the threshold frequency, right? Now let's move on to the question number 10, right? Moving on to the question number 10. Now you can see an electron is accelerated from rest through a potential difference of V volts, right? If the Broglie wavelength of the electron is 1.227 into 10 to the power minus 2 nanometer, or we can say 12.27 into 10 to the power 12.27 angstroms, right? So what we have to find is that if the de Broglie wavelength of an electron is accelerated from rest through a potential difference of V volts, if the de Broglie wavelength of the electron is the potential difference is, so we already calculated for an electron the de Broglie wavelength is nothing, it's 12.27 uh, into upon root V, right, in terms of the angstroms, right, in terms of the angstroms, right. So this is the de Broglie wavelength in terms of the angstroms, right. Now you can see here the de Broglie wavelength is given as the de Broglie wavelength lambda d is given as that's equal to 1.227 into 10 to the power minus 2 nanometer, right? Or we can write it as in terms of angstroms as 1.227, right? Into 10 to the power minus 10, right? Into 10 to the power minus 1, right? So this is this much of angstroms, that's 0 point, or we can write it as 12.27 into 10 to the power minus 2 angstroms, right? So this will be the what we call as this will be the de Broglie wavelength in terms of the angstroms, right? This will be the de Broglie wavelength in terms of angstroms, right? So 12.27 into 10 to the power minus 2 angstroms, or we can write it as 1.227 into 10 to the power 1.227 angstroms, right? Into 10 to the power minus 1, right? So this is the de Broglie wavelength in terms of the angstroms. So what we can do here is that I can see here. Uh, So it will be 12.27 into 10 to the power minus 2. That will be equal to 12.27 upon root V, right? So from here, this and this will get cancelled, right? But 10 to the power minus 2 is nothing. It's actually equal to 1 upon root V, right? 1 upon root. Now, if we scare on both sides, right? If we scare on both sides, scaring on both sides, it will be 10 to the power minus 4. It will be 1 upon V, right? So from here, V will be nothing. It will be equal to 10 to the power 4 volts, right? So this much will be the potential difference, right? 10 to the power 4 volts, right? So this much will be the potential difference through which the electron is accelerated, right? Let's move on to the next question, right? This is once again a very important question asked from your previous year exams. An electron of mass m with an initial velocity v naught is equal to v is equal to v naught I cap. It's along the positive x-axis. It enters an electric field, right, which is given as E is equal to minus E naught I cap, right? So it means that the direction of the electric field vector is opposite to the velocity, right? Or we can say the direction of the force will be along the direction of the velocity vector for the electron, right? So at time t equal to 0, so we have this electron, right? This is the velocity of electron, this along I cap direction, that's V naught I cap, right? The direction of this electric field is given along the reverse direction, that's minus E naught I cap, right? Minus E naught I cap. We know for electron, for negatively charged particles, the direction of the force is opposite to that of the electric field. So it will be along this direction will be the force on this electron, right? And the force on this electron will be nothing. It will be by magnitude E into E naught, right? E into E naught, right? Or we can say the acceleration of this electron will be nothing. It will be E naught upon mass of electron, right? This will be the acceleration of this electron, right? So it's given that at time t equal to 0, lambda naught is its de Broglie wavelength, right? So that de Broglie wavelength will be nothing. Lambda naught, that will be equal to h upon mv, right? That will be mv naught, right? Mv naught. Now at later time t, And now it's accelerating, right? At later time t, we know that the velocity at later time t is nothing. We can use this equation, v is equal to plus at, right? So u is nothing, that's v naught, plus acceleration is e naught upon m multiplied by t, right? So we can write this, the de Broglie wavelength at a later time t will be nothing h upon mv, right? It will be v naught plus e naught t upon m, right? So we can further solve it. So it will be mv naught, right? Me naught plus m and m will get cancelled, right? We'll be left with e naught t, right? E naught t, right? Now, from here we can replace this me naught in terms of lambda naught, right? So me naught will, we can replace. So this will be the new de Broglie wavelength, right? So if in terms of lambda naught we have to calculate it, right? What we can do here is we can replace h with lambda naught mv naught, right? So lambda will be nothing. It will be lambda naught mv naught, right? Upon mv naught plus e naught t, right? So this is how we can calculate the de Broglie wavelength at a later time t, right? Using the equation of motion, right? Now let's move on to the question number 12. The question number 12 is that when the light of frequency of 2 V naught, where V naught is the threshold frequency, right? V naught is the threshold frequency. It's given that V naught is nothing, it's the threshold frequency. When the light of frequency is 2 V naught, where V naught is the threshold frequency, is incident on a metal plate, the maximum velocity of electron emitted is V1, right? When the frequency of the incident radiation is increased to 5 V naught, the maximum velocity of electrons emitted from the same plate is V2. We have to find the ratio of V1 and V2, right? We know the kinetic energy, maximum kinetic energy will be nothing. It will be the incident energy minus the work function, right? Now you can see here, initially the incident energy was twice nu naught, right? It will be h 2h nu naught, right? Minus the work function, that will be h nu naught, right? So it will be equal to h nu naught. That's equal to the initial kinetic energy, that will be equal to half mv1 square, right? So similarly, for the second case, half mv2 square, we have the 5 times frequency, 5 times the threshold frequency, that will be 5h nu naught minus h nu naught, that will be equal to 4h nu naught, right? Now we have to calculate the ratio between V1 and V2, right? So what we'll do is we'll just divide the two, right? It will be half m will get cancelled. It will be V1 V2 or whole square, right? That will be equal to h nu naught upon 4h nu naught, right? So from here, uh, it will be equal to 1 upon 4, right? So V1 upon V2 or V1 ratio V2 will be nothing. It will be 1 ratio 2, right? It will be 1 ratio 2. The ratio between the two velocities will be 1 ratio 2. So moving on to the question number 13, the de Broglie wavelength of a neutron in thermal equilibrium with heavy water at temperature T and mass m is. And we know that for a monoatomic particle, right? For a monoatomic particle, the kinetic energy, the thermal kinetic energy is nothing. That's equal to 3 by 2 kT according to the law of equipartition of energy, right? So for 3 degrees of freedom, right? For 3 translational degrees of freedom, we will have 3 by 2 kT energy, right? 3 by 2 kT of energy, right? So this is the kinetic energy of, this will be the kinetic energy of the neutron, which is in thermal equilibrium with the heavy water at a temperature of T Kelvin and mass m, right? We know the de Broglie wavelength in terms of kinetic energy is nothing. It's h upon under root of 2 mke, right? So this is the de Broglie wavelength in terms of the kinetic energy, right? So you can just replace it. So 2 m 3 kt by 2, right? So from here 2 and 2 will get cancelled. So it will be h upon under root of 3 mkt, right? So this will be the de Broglie wavelength in terms of the temperature, right? In terms of the temperature. Now, looking on to the question number 14, and this will be the last question for this session, right? Electrons of mass m with de Broglie wavelength lambda fall on the target, right? So we have electrons. Let's suppose this is the electron of mass m, right? It's moving with some speed, right? It falls on the target, right? And once the electron falls on the target, it leads to the emission of the X-rays, right? it leads to the emission of the X-rays, right? Now the question is the cutoff wavelength, right? Means the minimum wavelength, right? Minimum wavelength that we can have, right? The minimum wavelength we can have for the X-rays is that so that all of the kinetic energy of the electron gets actually converted into the X-ray, right? Or it is emitted in the form of the radiation. That's the X-ray, right? That's the X-ray. So it means that if the electron is moved, or if the electron is actually moving against the potential difference of V, right? Through the potential difference of V, right? Then the kinetic energy of this electron will be nothing. That will be equal to E times V, right? And if whole of this kinetic energy gets converted into the X-ray upon the electron, when the electron actually hits the target, the kinetic energy of this electron gets converted, or gets converted into the electromagnetic radiation, right? Let's suppose it gets converted into X-ray, right? When highly moving or highly energetic electron actually strikes a target, the X-ray is produced, right? So minimum wavelength we can have is that all of this kinetic energy gets converted into the radiation, right? So in that case, the wavelength will be nothing. It will be equal to hc upon lambda, right? Hc upon lambda, right? Or we can say lambda naught will be nothing. It will be hc upon Ev, right? So hc upon Vv. So this will be the minimum wavelength, right? So that it gets actually full of the kinetic energy of the electron gets converted into the radiation, right? That's hc upon Ev. Here V is the potential difference through which the electron actually is accelerated, right? So that's it. The most of the portion, or each and every bit of photoelectric effect, or these are the most expected areas from the dual nature and photoelectric effect. The questions will be asked, right? So we have discussed some of the important PYQs as well, right? So that's it for the session, for this session today, right? In the next session, we'll be discussing with the atoms and nuclei, right? Till then, take care and goodbye.